I am going to go ahead and get started. I have seen the rumors on Twitter, and I can honestly tell you the answer is no. I did not write this talk to win a bet. A bet that said I got a $500 steak dinner if I won. And to win, I had to figure out how to bring the story of the electrocution of an elephant to a Ruby conference. The elephant part is true. It's relevant. You'll see. My name is Coraline Ehmke. I have 25 years of software development experience. I'm currently serving as an architect at a company called Stitch Fix. We're in the lobby. I am co-authoring a book called The Compassionate Coder. I am an open source troublemaker. This year I got into trouble by releasing my own ethical open source license called the Hippocratic License. And I've also launched the ethical source definition. I am fighting to give us as developers control of how our software is being used. If you're interested in the license, firsttoknowharm.dev. And if you're interested in the ethical source definition, ethicalsource.dev. I have a special treat for you. If you tweet about this talk and @mentionme, you'll be entered. Tweet something that you learned from the talk. I will pick the best answer and give you a giant Nikola Tesla bobblehead with a glow-in-the-dark light bulb in his hand. Let's meet our heroes. Thomas Alva Edison, born 1847. He was an American inventor credited with the invention of the phonograph, the motion picture camera, and the first practical light bulb. He registered over 1,000 patents in his lifetime, and he was what I call a direct current fanboy. Edison invested the money that he made from his early patents into what he called the Invention Factory, which is a facility in Menlo Park, New Jersey, and he staffed it with physicists, mechanics, engineers, and machinists. Edison's first patent was for an electrographic vote recorder in 1869. The problem he was trying to solve is that voting in a legislature takes a long time. So he thought he could improve it with automation. A man named DeWitt Roberts bought the patent for $100 and tried to sell it to Washington, but Washington, D.C. was not in favor of making the voting process any more efficient than it was because they wanted to make time for wheeling and dealing and filibustering. So young Edison's vote recorder was sent to the political graveyard. Nikola Tesla, born 1856, studied engineering and physics, but dropped out, like me, and died penniless in obscurity in New York City at the age of 86. He was rediscovered in the 90s and became something of a folk hero, and he was an alternating current aficionado. He worked from various labs around New York City through the 1890s to the 1900s, and this is a photograph of a lab he built in Colorado Springs in 1899 to study the conductive power of low-pressure air. He was trying to invent a way to send power through the air. Tesla applied for his first patent, which was an electric arc lamp, in 1884, immediately after leaving Edison's company and founding the Tesla Light and Manufacturing Company. We're going to talk a little bit about the war of the currents, but to get there, we need to understand something called a generator. In 1831, Michael Faraday discovered the operating principle of electromagnetic generators. The principle, later called Faraday's law, is that an electromotive force is generated in an electric conductor that is subject to a varying magnetic flux, a wire moving through a magnetic field. He built the first electromagnetic generator called the Faraday disk using a copper disk rotating between the poles of a magnet, and it produced a small DC voltage. That same year, a man named, and I'm not making this up, Hippolyte Pixie, improved the generator by using a wire-wound horseshoe with the extra coils of the conductor generating more current, but his generator was AC, and that was considered a major flaw at the time. William Cooke and Charles Wheatstone were a pair of inventors who made their name with improvements to their telegraph. They also made an important improvement in generators by replacing the permanent magnet with a battery-powered electromagnet. They patented that invention in 1845, and by the 1860s, this kind of generator was common. The first practical generator capable of powering electric devices was called the Graham machine. It was created by Z.T. Graham, a Belgian inventor, and he started selling these inventions in the 1870s. A demonstration of arc lighting took place at the 1878 Paris expedition, and it triggered a steep sell-off of gas utility stocks. The world was waking up to the potential of electric power. Which brings us to the War of the Currents. Edison stubbornly held on to the idea that direct current was the best way to deliver electrical power to the world, while Tesla believed in the superiority of alternating current, and the War of the Currents raged for nearly 20 years. The first large-scale power station in America was Edison's Pearl Street station in New York City, which began operating in 1882. The station had 6 200-horsepower dynamos, each powered by a separate steam engine. It was located in a business and commercial district and supplied 110-volt electricity to 85 customers, powering 400 electric lamps. But Edison's direct current generators were terribly inefficient, and they couldn't deliver power over distances of more than a few city blocks. So in order to light New York City with Edison's generators, there would have to be a power station every 5 or 6 blocks. In 1884, at the suggestion of a friend, Edison hired Nikola Tesla to improve his DC generators, and he offered him a reward of $50,000, which in modern terms is about $1.2 million. Even though Tesla thought that DC generators had no future, he needed the work, and so he set to work. And he did, in fact, improve DC generators significantly. When he went to claim his reward, Edison laughed at him and said, "My friend, you don't understand American humor. I never intended to give you $50,000 for this work." Tesla was devastated, and he had to resort to digging ditches and doing odd jobs to raise enough money to start his own company, Tesla Electric Light and Manufacturing. He tried to come up with a better way of generating alternate current, and he developed a steam-powered reciprocating electricity generator. Steam was forced through the bottom of the oscillator and rushed out through a series of ports, which pushed a piston up and down, and that was attached to an armature with a magnet on it. And the magnet vibrated at high speed, producing an alternating magnetic field. This induced alternating current in the wire alternating current in the wire coils and did away with the complicated parts of a steam engine generator, but no one was interested in his invention. But Tesla's invention was saved from obscurity when it caught the attention of engineers at Westinghouse Electric. Westinghouse Electric invited Tesla to participate in the 1893 World Columbian Expedition in Chicago, where they had a lot of space in a building devoted to electrical exhibits. Westinghouse won the bid to light the expedition with alternating current, and it was a key event in the history of AC power, demonstrating to the American public the viability and safety of AC. By 1902, 61% of generating capacity in the US was AC, and that increased to 95% by 1917. AC was really good at delivering power over long distances, so it was possible to connect different stations and balance the load between them. The War of the Currents was won through a partnership between Nikola Tesla and George Westinghouse. Edison, who finally admitted defeat, shifted his focus to other inventions. Today, the world consumes an estimated 157.5 petawatt hours of power, and electricity is responsible for 10% of the world's GDP. I mentioned at the beginning an elephant. There's a term in French that I'm not going to attempt to pronounce, Literally translated, it means the spirit of a staircase. In 1773, the French philosopher Denis Diderot was at a dinner party, and someone insulted him, and it left him speechless and ruined his whole night. And when he finally left to go home, he was going down the stairs, and he came up with the perfect retort. And he was so frustrated because he's like, if I thought of this an hour ago, I could have saved my evening and made a good point and defended myself. So Edison had one of these spirit of the staircase moments too. He demonstrated this in a 1903 film called Electrocuting the Elephant. Edison, for the past 15 years, had been experimenting with electricity as a humane way to put animals down. And this method of killing animals was generally accepted by the animal rights activists of the time. This is Topsy. Topsy was a circus elephant and something of a problem child. She had killed a spectator at the circus, but he deserved it. He put out a cigar on her trunk, and she attacked him. Topsy had also attacked several handlers, though, and the circus decided that she was too much of a liability, and they decided to put her down. The event was captured and released by the Edison Film Company as a 74-second silent film in 1903. And interestingly, this is the first time that death was captured on film on any kind of camera. Edison's film shows the euthanization of Topsy in an under construction fairground in Coney Island. And when the film was being promoted, Edison was very clear about the fact that AC current was used to electrocute the elephant. He just could not let it go. My friend Max said when I was discussing this, the fact is, if you have to murder an elephant publicly to make your point, you're likely on the wrong side of whatever it is you're trying to argue. Both Edison and Tesla are portrayed in history as lone geniuses, turning out invention after invention, but this wasn't really true. In fact, the notion of a lone genius is a relatively new concept that comes from the Enlightenment of the 18th century. In previous centuries, invention was acknowledged as a collaborative process that built on the historical work of historical precedent by other scientists. But when Britain enacted the first copyright law in 1710, it gave credence to the idea of inventors as the originators and owners of their ideas. Harvard scholar Marjorie Garber wrote in an 1987 book, Shakespeare's Ghostwriters, that it was during the Romantic era that the cult of the genius emerged. And Shakespeare is held up as a prime example of the type. There's lots of evidence that he borrowed heavily from other poets and playwrights and collaborated extensively, but he's held up as an example of natural genius. In his book, The Powers of Two, author and essayist Joshua Schenck responds to the myth of the lone genius by exploring the role of partnership and collaboration. Success through collaboration extends beyond widely acknowledged duos like the Wright brothers or the Curies. In his book, he emphasizes that success arises from creative and innovative relationships. In some cases, these relationships are collaborative, and in others, they're adversarial, but they always have an undeniable interpersonal component. Edison, as I mentioned, got to start making improvements in telegraphy, and he sold his patents and used that as leverage to build a company. And he had his invention factory. And the physicists and machinists and mechanical engineers who worked at the invention factory were called muckers. And it was the muckers who were responsible for generating the hundreds of patents that are credited to Edison. The muckers didn't enjoy wide commercial success for their inventions at first. They quickly discovered that when they tied an invention to Edison's name, the audience responded better because the audience liked the idea of this lone genius working and turning out these technological marvels. Francis Gell, who was one of Edison's longtime assistants, even wrote that Edison is in truth a collective noun. Tesla worked solo for a lot of his career, and he failed to meet with success. He needed the support and business acumen of men like Westinghouse to make his inventions practical. And there are lots of other examples of collaboration throughout history. We have Alan Turing, but Alan Turing would not have been successful if not for the dozens of uncredited women who worked on the bombs to decode German encryption. Ada Lovelace needed Charles Babbage, without whose mechanical computer her programs would have nowhere to run. And Steve Jobs is lionized for the revolution of the personal computer, but he relied heavily in his partnership with Steve Wozniak. The conclusion that Schenck comes to is that working relationships are the fundamental engine of the creative process. So what does all this have to do with software development? In a paper called Human Cumulative Culture, published by researchers in cognitive evolution and biology at the University of St. Andrews, they explore the unambiguously cumulative character of complex human advancement. The paper describes how the transmission of knowledge gives traits that are more complex than a lone individual could develop on their own, leading to what they call a ratcheting effect on technology capabilities. The authors argue that understanding the progress of human endeavors is only possible by looking at social processes. And they describe something called pro-social behaviors. There's a broad range of altruistic and reciprocal social processes that fall into pro-social behavior. They're defined as voluntary actions intended to benefit other individuals or society as a whole. And examples include altruism, obeying rules, acting on our values, and most importantly, practicing empathy. As developers, we feel good about our code when it's new. And with the exception of test-driven developer enthusiasts, we may be less enthusiastic about doing things like writing tests, writing documentation, writing proof that our code actually works. And this is evidenced by the hundreds of thousands of empty READMEs on GitHub. But if you're part of a project that is innovative and beneficial to society, that helps you get through the boring work. Successful software requires collaboration with stakeholders, fellow coders, designers, technical writers, managers, and of course, end users. Even in the open source world, where we're often motivated by satisfying a need that we ourselves have, projects don't often get success without the assistance of other people, collaborating in the code base, writing documentation, giving talks, or even writing books. I believe that each and every one of us alternates on a spectrum between the raw creative power of Tesla and the practical and methodical approach of Edison. So which one are you? A Tesla developer prefers to work alone without interruption. And they're really good at solving complex problems in a really creative way. They may not like writing tests or documentation, and they work in bursts of energy followed by long periods of low productivity. The Edison developer, on the other hand, loves pair programming and may apply architectural patterns to their work. They write comprehensive issue descriptions, and they produce work at a steady velocity. So when you ask yourself where you fall on a Edison-Tesla scale, you may aspire to be more like one or the other, or you may recognize that you move between these extremes in different situations. And that's actually the ideal. The best developers I know oscillate between Tesla and Edison as the situation demands to solve the problem at hand. But if you identify more with Edison or more with Tesla, there are different strategies you can employ to emphasize your strengths and work around your weaknesses. Edison was a practical man, really good at execution, but also very resistant to change. If you're an Edison, make use of your practical tendencies, learn from your failures, embrace teamwork, but don't fight against radical ideas. Work to make those ideas successful. Tesla was one of the world's most creative problem solvers, and he was not bound by convention, but he was very naive. If you're a Tesla, don't let people tell you that your idea won't work or that it's impractical. Find a way. Believe in yourself even when no one else does. And most importantly, figure out a way to build partnerships to make your ideas take shape and change the world. We all generally work at companies with established technology platforms. We have a standard stack that we work in, but sometimes we're attracted to new frameworks or new technologies or new languages, and we want to bring those into our workplace. How do we do this in a responsible way? How do we build our own invention factory? There are three main aspects to innovating responsibly with technologies in a workplace. You want to evaluate the need for the new technology, test it through experimentation, and then follow a decision-making matrix to make sure that it gets adopted. First off, evaluating the need. There are 6 primary questions that we ask ourselves. Ask yourself, why is this new problem a priority? What's different about what you're facing now compared to what you faced when your stack was first chosen? And tie it to a business need. If you can't tie it to a business need, you're not likely to get buy-in from stakeholders. Be very clear about why your current approach is not working. Why isn't the stack that you've been using forever or the language that you've been using forever unable to solve the problem at hand? And be very clear about having exhausted the possibilities of working with your existing technology. And think about what has changed. Think about what kind of effort is needed to solve the new problem. There are 2 categories of effort. There are 2 categories of effort that you can divide into. One effort is a strengthening effort, which means investing time and energy to make an older technology do something new through re-engineering or process changes. Sometimes these efforts pay off, but sometimes you end up being like Edison trying to improve the DC generator. It can be a lost cause. Growth efforts involve using new technologies to solve a problem. But growth efforts may fail if clear parameters are not established up front. You could end up like Tesla, making inventions that were unsaleable, that nobody wanted. To help us at Stitch Fix understand when to bring in our new technology, I created this, the Technology Adoption Matrix, with distinct axes for adoption and utility. Ease of adoption we'll start with, and that encompasses a number of considerations. Does the new technology fit within our existing processes? Will it be easy for other developers to learn to use it effectively? Is there good documentation? Is there prior art that we can learn from? Are people responding to questions about the technology on Stack Overflow? Is it more flexible than our current tools? Does it have a strong security story? Have we considered the overall cost of adopting the new technology? Usefulness can be determined with another series of questions. Does the technology enhance the performance of our teams? Does it positively impact stability, performance, and reliability? Is it well maintained? Does it have an active user base? Does it solve the problem more effectively than our current tool set? We can use this matrix to guide our decision-making process. In the first quadrant, reject, this is where technologies that are difficult to adopt and provide a limited utility fall, and you can reject those outright. Easy to adopt solutions that maybe are limited in their capacity aren't likely to be adopted, but they can be really useful to play with. That creates learning opportunities that can help us gain a new perspective on the problem that we're trying to solve. Technologies that are useful but difficult to adopt fall into the wait category. They may be candidates for future adoption once the technology matures to the point that tooling and training exists to make onboarding easier. And finally, in the Explore quadrant, solutions that are easy to adopt and accommodate a wide range of use cases. Technologies like this can move into the next phase, which is experimentation. To inform and guide the evolution of our solutions in a framework of pragmatic innovation and creativity, we sometimes experiment with new ways of doing things, and we should do so responsibly. So what are the characteristics of a responsible experiment? First of all, make sure that you can clearly state what the problem is. If you can't state what the problem is in a sentence or two, you probably don't understand it sufficiently. When you're conducting your experiment, you want to make sure that it has minimal impact on other systems. For example, if you have a service-oriented architecture and you want to experiment with protobuf, you don't want to have to change every other service that might be talking to your service to support protobuf. You want to limit that footprint. And that ties into establishing boundaries. You want to make sure that you're testing exactly what needs to be tested. You want to establish clear success criteria up front. It's possible that during the course of the experiment, you fall in love with this new technology and you lose sight of the pragmatic approach that is probably going to be most successful. You want to constrain the time and cost time box and make sure that whatever you do can be rolled back quickly. If you're on a deadline, that's not the time to experiment. The best engineering cultures empower us as engineers. They give us flexibility in the way that we go about solving problems. But sometimes what we want to change has an impact outside of our immediate situation. We have to be careful and thoughtful about how other engineers will be affected. And for this, we can use the RACI framework, which stands for responsible, accountable, consulted, and informed. So the first thing to do is to identify the scope of the change you're trying to make. If it only affects your team, that's a limited scope and it's a little bit easier. The person responsible is you or whoever you're pairing with. Your manager is accountable, and maybe that's in collaboration with other senior engineers. You want to consult other members of your team. You don't want to surprise them. And it might also make sense to inform other engineers on other teams about what you're doing. They may have a similar problem, and they may be very interested to see what you learn from your experiment. If you're making a larger change that's going to affect your entire engineering organization, there's a different set of decision makers. The people who are responsible is you and a small team of engineers that you're working from, preferably taken from different teams across your organization. Those teams' managers and senior engineers are accountable, and you want to make sure that you consult with senior engineers across the org and also think about the impact of your change on ops and security. And you want to make sure that you're informing the broader engineering organization about everything you're doing because it's going to impact them. One thing that I struggle with personally is I feel a need to drive to consensus. I want everyone to agree that what I'm proposing is the best possible solution to a problem, but I'm often wrong. So I want to get feedback from other people to validate my experiments, to validate my instinct about how to solve the problem. And that sometimes can lead to a problem where if I don't have full consensus, if everybody isn't fully on board, I might think that my idea isn't a good one. But as engineers, we are empowered with a certain level of decision making. Don't be afraid to make decisions even if everyone doesn't agree. Final thoughts. We can't just be an Edison or just be a Tesla if we want to be successful. We have to find a balance. If we stubbornly hold on to our own ideas and ignore evidence to the contrary, we might find ourselves left behind, like Edison during the current wars. But if we don't partner with people who complement our ingenuity, we might end up spending our lives and our work hours building things that nobody really wants. Teslas solve impossible problems, and Edisons make solutions practical. And as I mentioned, the best developers oscillate between these two extremes. If you're wondering if I'm more of a Tesla or more of an Edison, that's on my left shoulder. Nicola Tesla with devil horns. On the right-hand side, I have Ada Lovelace with a halo. A lot of the content from this talk was condensed from a blog post that I wrote, and you can find it on my blog, where.coraline.co/blog. I want to thank you for being my audience today and point out that I have a ton of stickers up here, so please come up and grab one. And if you have questions for me, please come up and ask them. You can find me on Twitter at Coraline Ada. or my website at where.coraline.codes. And if you're interested in ethical open source, check out ethicalsource.dev. I'm also setting up a Birds of a Feather session to talk about how we can bring ethics to the open source world. Thank you.